So we've seen principal ideals, which are sort of ideals that come from a single element. If we have more than one element, though, we can still try to look at ideals that are generated by those. So suppose we have a commutative ring and we have some finite number of elements in R. Then the ideal generated by these generators, A1 through AN, is the set A1, A2, AN. So we just put them in a list and then put parentheses around the list. And it's a collection of all sort of R linear combinations of the A's. So the R's can be any number or any element of our ring. So that's the ideal generated by a set. And notice that if there's just one element, this is just consistent with what happens with a single generator. And so what we do is we just tack on more of the expressions that were involved in principally generated ideals. So let's do an example. And we're going to do an example showing that sometimes, even if you have more than one generators, it's not necessarily the case that you need all of those generators. And then we're going to prove a theorem in the next video, and then we're going to do an example showing that sometimes you do need all of the generators. All right, so what's our example? Let's look at the ideal generated by 4 and 6 in Z. So what is this? The ideal generated by 4 and 6 is a collection of all, let's see, I'm going to write it like this, Z linear combinations of 4 and 6. So I'm going to put the elements of our ring on the right instead of the left. Now, this should look familiar. In particular, we investigated combinations of two elements before, and that led us to Bezout's identity. So, what we can see here, or what we can recall, is that the GCD of 4 and 6, at least, is, well, first of all, it's 2, and by Bezout's identity, or Bezout's theorem, however you want to call it, there exist A and B in Z such that 4A plus 2B, or 6B rather, is the GCD, is 2. So what this tells us then is that 2 is actually an element of 4 and 6. And in fact, we could even write out what those A's and B's are, right? 4, negative 4 plus 6 is 2. So 2 is actually an element of 4 and 6. And since any multiple of 2 is therefore also an element of 4 or 6, then we actually have a subset inclusion. So the principal ideal generated by 2, that is all multiples of 2, must therefore also be a subset of the ideal generated by 4 and 6. And in fact, the converse of this is true. So the converse is true. Well, the reverse inclusion is true. Let me put it like that. And this is actually easy to see here because if you have an element of the left ideal, some 4x plus 6y, you can write that as twice 2x plus 3y. And so it must also be in 2. Okay, so we have a double containment here. So this tells us then that the principal ideal generated by 2 is the same as the ideal generated by 4 and 6. And in fact, in Z, this will always happen. And this is the subject of our very last week. So we're going to return to this when we talk about what are called principal ideal domains at the end of chapter 3. But this will always happen. That is, well, in Z, not always happen, but in Z. Oh, I already have the in Z, sorry. This will always happen, and that is that if you look at the principal ideal generated by, sorry, the ideal generated by A1 through AN, that's going to be the same as the principal ideal generated by the GCD. Right? So, in fact, in Z, all finitely generated ideals, so if you are generated by a finite number of elements, you're called finitely generated, are principal.